just area between curves.
Okay. What are the two functions?
So it's x equals -3 and x equals 4. And the first function is 2e to the 2x. And the second function is e to the 2x, and then aside from the exponent, plus 1. So not in the exponent.
Oh, sorry. I was trying to figure out what that meant.
That's why.
It is hard to verbalize that. I'm not sure I know how to verbalize that. E to the 2x plus 1. Yeah. I guess if it was in the exponent, you'd have to say e to the quantity 2x plus 1. So if you just say e to the 2x plus 1, that should be this. All right. Well, it's always a little helpful. In fact, it's very helpful to have these graphed. And the reason being is to know which curve is on top. Now this one, when x is 0, this is 2, so it starts at the same point, and it's not going to be as steep, so it's going to go something like that. We're going to go from, let's see, probably looks like that. So we want the area between these two curves. Now, if I have drawn it correctly, where left of the y-axis, this curve is on top, and to the right of the y-axis, the other curve is on top. If that's correct, then what I need to do is integrate this in 2 steps. The first step has to be this curve minus that curve going from -3 to 0. And the second step has to be the top curve minus the bottom curve going from 0 to 4.
Okay. And I have the answer too if you want to just write that down somewhere.
Yeah, what is it?
1,488.48.
Okay. Do they mind if we do this with a calculator?
No, I don't think so.
In other words, you would be able to use Mint.
Yeah, I'm not familiar with
How
that.
you're not familiar with how to use that on your calculator? No. This is not that difficult to integrate. We can manually integrate this. Now, first of all, let's go back and analyze this. I'm not 100% sure of that. So what I really should do is graph these two curves on Wolfram alpha and see what happens. But I'm 95% sure this is the case. And we can find out easy enough. So the first integral is the bottom function minus the top function, and we're going to add to that, and this is going to go from -3 to 0. We're going to add to that going from 0 to 4 of 2e to the 2x minus e to the 2x plus 1. Okay? You understand that part?
Yes.
Okay. So let's see, the integral of that is e to the 2x divided by 2 plus x minus 2e to the 2x divided by 2 plus e to the 2x divided by 2. Let's make sure we do this. Minus e to the 2x divided by 2 plus x. So if I remove the brackets, makes this a negative and makes this a negative. And we want to evaluate that. Let's see, I screwed up here already. I think I can do this. I need to evaluate that from -3 to 0. And we're adding, okay, I think I got this right. We're going to evaluate this from 0 to 4. So let's see, when we do 0, we have 1/2 plus 0 minus 1. And I have to subtract the evaluation at -3. So that would be e to the minus 6x over 2 minus 3. I guess I could have simplified this. Plus, no, I'm going to plus e to the minus 6, and it means 6x here, I'm not minus 6. And then plus e to the 8th minus e to the 8th over 2 minus 4. And then minus when it's 0, this is 1 minus 1/2. So that becomes 1/2. So I got to minus
scroll down a little bit, please?
Yeah. All right. So that sure doesn't look like, how many is it supposed to be? 1488? Well, maybe it is. Notice what's going to override everything here. That.
So the one you circled right next to that, that's e over what?
E to the 8th over 2.
Over 2, okay.
So actually, if I combine the e to the 8th minus e to the 8th over 2, I get e to the 8th over 2. So I can do this, just simplifying it. Notice that that's a small negative number. These are going to be small numbers because e to the minus 6th is going to be a very small number. Everything's a small number here except this right there. So what is e to the 8th over 2? Let me bring up Wolfram.
$1490.478.
So what do you want to bet? That everything else is 2 minus 2. We have a minus 1/2 there, plus 3 here, and looks like we have a minus 4.5 there. That and that are minus 5. That makes minus 2. So if we take your answer, and subtract 2 from it, we get the answer. We take your 1490, subtract 2, we get this answer after rounding it up. Now, was there anything about my explanation that you didn't get?
No, I have it all down too. It's easy to
Okay.
follow.
It's mainly keeping track of your negative signs. It really is. I hate to say that, but when you're doing integration like this and you have to come up with a number, if you have to do it manually, just make sure you use more parentheses, not less. In other words, use parentheses even when you don't need them, just to make sure you don't lose a minus sign. That becomes the secret to getting the answer. Figuring out what happens here when x is negative isn't that hard. We can tell that when x is negative, this plus 1 is going to rule, because 2 times e to a negative exponent is going to be a very small number. Whereas as soon as I add 1 to that small number, it's going to be a lot higher. So the curve on the left of the y-axis that's above is this one right here, for sure.
Okay.
But you could have also determined that by just graphing them and watched what happened. All right.
All right. So the next question, it says, use n equals 4 to approximate the value of the integral by the following methods: trapezoidal rule, Simpson's rule, and find the exact value by integration. And the function is the integral symbol with it's 5 on top, 1 on the bottom. And then it's 5 over 9 minus x dx.
What's the rest of it? Oh, dx. Okay.
And that's all.
All right. Let's have a look at this thing. Let me plot it. 5 over 9 minus x. Okay, it's hyperbolic in nature. And we're going from 1 to 5. So we're in this area right here. So this thing, if I were to draw it, looks something like this. This being 1, over here being 5. I get that right, yeah, the vertical asymptote is at x equal 9. So our entire area of interest is between the y-axis and 9. So to use the trapezoidal method, where n is 4, means I'm going to use 4 trapezoids. One of them is going to look like this. The rest are going to look like this. Oops. Okay. So I have to sum up those trapezoids. What's the area of each trapezoid? What's the formula for the area of a trapezoid?
Ooh, see if I remember it. Gosh,
If
I
I
don't
drew
remember
the
it.
trapezoid like this, what's the area of that trapezoid?
So you do
Average
base
height,
times height.
base, it's the average base, because we have two different bases. We have a base 2 and a base 1. So it's the average base. So it's the average base, which is base 1 plus base 2 divided by 2, that's the average base, times the height. That's the area of a trapezoid. Well, notice that these trapezoids are on their end. In other words, if I were to draw the trapezoid like these trapezoids, they're like this. So the area of the first trapezoid, what's the base 1? If this is f of x, what would I call the base 1?
1.
Well, that's where it begins, but this measurement is f of 1. So base 1 is f of 1. You see why?
Yeah.
When I plug in 1, I get 5/8. So on the y-axis, this is 5/8. So base 1 is 5/8. What is base 2?
5/7.
So the area of our first trapezoid is 5/8 plus 5/7 divided by 2, and what's the height of that trapezoid?
5/8.
No, notice that it's on its side. So to get the height, you have to go horizontally.
1.
Yeah. So that's the area of the first trapezoid. The area of the second trapezoid, notice that we use this now as base 1, and this is base 2. So base 1 is f of 2, and base 2 is f of 3. And the height of each one of these trapezoids is 1, so we really just need the average. And if we, there's a formula for the trapezoidal method, but it's really quite useful to understand why it's there. So that's why I'm going to the trouble of explaining it all. Hold on. So I'm going to have the average of 5/8 plus 5/7, and then I'm going to have the average of 5/7 plus 5/6. Then I'm going to have the average, oops, excuse me, no, that's not quite right. Let's see, this point here was 5/7. Yeah, and then the next one, it is going to be 5/6. And the one above that is 5/5 or 1. So in effect, what we have is the following. 5/8 plus 5/7 divided by 2, that's the area of the first trapezoid, plus 5/7 plus, and this height here, yeah, is 5/6. Plus, so that's that one, that one. The third one has f of 3 as its base, which is 5/6 plus f of 4, 1. Now let's write that as 5/5 so we understand exactly what we're doing. And the fourth one is 5/5 plus 5/4 divided by 2. So you see what can you read that? I don't know.
Yeah, I can.
Okay. Now there is a formula, and let me write it, and you can see why this is the formula for the trapezoidal method. It's b minus a over n times f of x plus 2 f of x sub, excuse me, that's f of x sub 0. This is f of x sub 1 plus 2 f of x sub 2 plus, in our case, 2, no, the last one is only used once again. So in our case, the fourth one is f of x sub 3. So there's the formula for the area using the trapezoidal rule. And notice what's going on here. We used that one once. We use all the others twice except the last one, which we use once. And why is that? Well, if you look at the picture, this first base is only used in one of the trapezoids. This base here is used in 2 different trapezoids, as this one is here, and the third one. So we need a fourth one. I've only got 3 there. So there's a middle one here, which is 2f of x sub 3 plus f of x sub 4. Yeah, there's 5 bases. F of x sub 0, this is base 1. F of x sub 1 was base 2. F of x sub 3 was base 3, that was base 4, and this was base 5. And notice that there are indeed 5 bases. 1, 2, 3, 4, 5 bases. And this part over here takes care of 5 minus 1, there's b minus a, divided by 4. So I'm multiplying everything by 1. Notice that if we had more intervals, the height of the trapezoid would be smaller.
Where'd you get over?
Over 4, because I said use n of 4. When I use n of 4, it means I'm breaking this up into 4 trapezoids.
Okay. And the b 5 minus 1, that's just the intervals?
They wanted us to integrate from 1 to 5.
1 to 5, okay.
So this first base here starts at 1. It goes from 1 to 2. And then the next trapezoid goes from 2 to 3. So if we figure this out based on their formula, it's actually a little bit easier. We don't have to go through and find the average between those fractions. This is base 1. I only use f of x sub 0 once, so that's 5/8 plus 2 times 5/7 plus 2 times 5/6 plus 2 times 5/5 plus 1 times 5/4. That very last base of the far right trapezoid there, this amount that I have circled here on the right, that is f of 5, which is 5/4. This still isn't the easiest. I am going to have to add these ridiculous fractions that they gave me. Do we need a number? Can you do this in your calculator? You should be able to do this part here easy enough.
Yeah.
Let's have a number for that. Be around 6. Maybe 7. Yeah, almost. It should be very close to 7.
Well, I hope not, because the answer they give us is d of x equals 3.485.
That sounds like this divided by 2. And did you get a decimal or a fraction when you added these up?
I'm getting a decimal, but I'm still going with it.
Let me guess, that decimal is 7.97. That's because I gave you the formula wrong. It's b minus a divided by 2n. So we need to take this number and divide it by 2.
Yeah, the decimal was 6.97 divided by 2 is 3.485.
Yeah. Did you hear what I said? I gave it to you wrong the first time. It's b minus a divided by 2n.
Yeah.
And the 2 came from all of these 2's in the denominator here when we did it manually without using the formula. Okay. So are we good with the trapezoidal rule?
Yep.
Okay, let's look at Simpson's rule. Now, the difference between Simpson's rule is he uses parabolas instead of trapezoidal edges. In other words, we can kind of see that trapezoids work better than rectangles, right? I mean, in my drawing here, if we were to use rectangles, we would have a lot more empty or leftover space or extra unused space. So trapezoids work better than rectangles, but what works...
Scroll down.
Yeah, what works better yet is instead of using a straight edge on the curved part, we're going to use a parabolic shape.
Okay.
Which will more closely match the curve we're dealing with. Now, I'm not going to go through the math of each parabola, but there's a formula much like the trapezoidal formula, only it's the Simpson's formula. Let me give that to you. This is the trap formula. And Simpson's formula is b minus a divided by 3n times f of x sub 0 plus 4 f of x sub 1 plus 2 f of x sub 2 plus 4 f of x sub 3, and then the last one has just 1 again, plus f of x sub 4. Okay, so 5 minus 1 divided by 12 times, what was our first one? It was 5/8.
5/8. Yep.
Plus 4 times 5/7 plus 2 times 5/6 plus 4 times 5/5 plus 5/4. So this is 1/3 on the outside. And the inside number is now going to be different. If you could do this on your calculator.
Yeah, so I'll see if we set it up right, but the answer is 3.466.
Okay, so this is the number 4. So what was that answer again? Read it and I'll write it.
3.466.
Okay. So add these 4 or 5 numbers together and see if you get 10 something. Pretty sure you will.
Yeah, 10.3.
And then divide that by 3.
3.466.
Okay.
It's a lot easier.
Now, the third way they wanted was the exact way.
Correct.
I'm sure a lot of people find it amazing that we still spend all this energy learning how they used to have to approximate it. Whoops. Doesn't that bother you a little bit, given that nobody ever uses the trapezoidal method anymore?
Yeah.
Well, actually they do, believe it or not. There are some functions you can't integrate. So sometimes you have to use the trapezoidal method to come up with an approximation of them. So I want to do what? The exact method. Don't need a picture anymore. I just need to integrate that. Well, let's make it a little bit easier. Let's remove the 5. Notice I can't take out the 9 yet. What's the integral of that?
Natural log of something I forgot.
Well,
We need
whatever's
90x.
in the denominator. But now you have to divide that by the derivative of the bottom. You see why? In other words, take the derivative of that. What do you get? You get 1 over 9 minus x, but now I got to take the derivative of the inside, which is minus 1. So it actually turns that into that. So this cannot be our antiderivative because its derivative is not what we started with. So in order to get this to be the integral of this, I have to divide it by the derivative of whatever's inside. In other words, I'm really using u substitution with u being 9 minus x. I'm just not calling it that. So it's minus the natural log of 9 minus x. Okay. And we're going to evaluate that from 1 to 5. And there's still this 5 out there, so let me put that in there. You know how to evaluate these? Are you good at this?
No.
Okay, you start by substituting the top number in for x. So we get minus 5 natural log of 4. And then the next step is to subtract everything that you get when you substitute the bottom number in. Well, that is what? A minus 5 natural log of 8. So our exact answer is minus 5 natural log of 4 plus 5 natural log of 8. I didn't write down other answers, but this number better come awfully close to Simpson's answer, which was 3 point something.
It's actually the same thing.
Oh, is it?
Yeah.
Wow. That's pretty impressive that Simpson's is that accurate. Only using 4 intervals. That's amazing. Although not so much with this function, because if you think about it, this function is very parabolic looking. So if you're using parabolas at the top to approximate those areas, it should be very accurate. And it is. It's like the most accurate method I know of is Simpson's method. All right.
All right, cool. Let's see that one.
Yeah. Okay.
Alright, we have another area between the curves, a little different this time.
Okay.
So the first function, y equals 9x. And the second is y equals x squared minus 10. And then x equals negative 2, x equals 1.
X squared minus 10 is that. Y equal 9x is a straight line with a very steep slope. We're going from minus 2. Well, actually, these are vertical lines, right?
Yeah.
Okay. This curve here, y equal 9x, appears to be above everywhere that we're concerned about. In other words, we're looking for this area here. And throughout that whole area, the above curve is the y equal 9x. The below curve is the x squared minus 10. What are these intersection points? This point right here is interesting because if this point is less than minus 2, then we also have this area right here to worry about, where the second curve is over the other curve. So how do we figure out where these intersect?
Set them equal to each other?
Yeah, yes, exactly. X squared minus 10 equals 9x. How do we solve that?
Take the square root.
No, treat it as a quadratic.
Quadratic.
Factor. We have x minus 10, x plus 1. So our intersection points, if those cross up here at x equal 10, we don't much care about that. That's way outside of the area we're interested in. But the other point it crosses is x equal minus 1, right here. So this point here that I put a big dot on is in our picture. So the first area that I shaded in was not correct. It's this little triangular piece to the left of that dot plus the other. So how am I going to do this? What's my first interval going to be? And from what to what?
-1 to 3.
No, we're going to go from this point on the x-axis, which is -2, to this point on the x-axis, which is -1. Okay, you always go from bottom to up.
Okay.
Okay? And, I'm sorry, from left to right and from bottom to top. What am I going to integrate in that small interval? Which function is on top?
Y equals 9x.
No. Notice that it's not on top in this little portion right here. X squared minus 10 is on top. So it's going to be x squared minus 10 minus the other function. So that's going to give me this little area right there. I'm going to add to that, since they want the total area, right?
Yep.
And they want the absolute area, right?
Yeah, I think so.
Yeah.
Let's see.
Okay.
Yeah, the final answer is 151/6.
Okay. What's the next integral limit's going to be?
The next one will be
From -1 to what?
-1 to 1.
Exactly. Because we're going from this point here now to this point here. And in that whole interval, from here to here, 9x is on top. And here's where you want to make sure you use your parentheses, otherwise you're going to get the sign on this constant term wrong. Okay? So that's our answer, whatever that number is. So let me erase, and let me not erase that. Let's do that real quickly. I need more room. Let's integrate it first. Integrate this for me.
Okay, so I'm getting my terms mixed up again. Integrate and...
When you integrate, you add 1 to the exponent and divide by the new exponent.
So that's x cubed divided by 3 minus 10x.
Okay, let's put this term second, despite how I wrote it.
Okay. Minus 9x squared over 2. And then minus 10x.
Okay, so that's that integral that we have to evaluate from -2 to 1. So I'm going to write all of that very small right in that area there. So help me do that. How do I evaluate it from -2 to 1?
What do you mean?
In other words, we have to do this right now. We integrated the function, got this, and now we have to evaluate it between its limits of integration. Excuse me, it's -2 to -1. Sorry, that's probably what confused you. Okay, plug in the top number first for x, figure out what we get. What do you get?
The top number is in -1.
Yes.
Okay. So it would be -1/3 minus 9/2. 1/10.
Plus 10.
Okay.
We're plugging in minus 1 for x.
Oh, okay.
Okay, so that is the top limit of integration evaluated. We want to subtract from that what we get when we plug in the bottom number. When you plug in minus 2, what do you get?
So I'm trying to figure out how to write this with the little piece of paper I have.
Yeah, I know. That's one of the big problems with calculus. At one point, I switched from letter-size paper to legal-size paper because of calculus, because all the problems were more than one page. I've never been very good at writing small.
So what did you say, like, the term was for plugging in the -1, the top interval?
Evaluating it at one of the limits. You're integrating the function and then evaluating it at the upper limit. And then you're going to subtract from that evaluation the evaluation of this function at the lower limit. So we've done the upper limit evaluation. It's that number there. And now we're subtracting off what we're going to get when we plug in the lower limit, minus 2, into this thing. What's the first term?
Okay. So minus 2 would be -2/3. No, excuse me.
-8/3. Okay, minus, when I plug in minus 2 here,
-18.
and finally, when I plug it in, it's that. Okay? Now, observe what we're looking at here. This is always the case where you have tons of negative signs. And that's why it's so important to use the parentheses here.
Is there a reason? Oh, I was looking at, okay. On the outside of the, when we evaluated at -1, the -2 right outside the bracket, I thought we were multiplying that.
Now, I almost erased that. That's the lower limit of my integration. That's not part of our problem. Okay, so now we need to convert each of these to numbers. This is pretty easy over here. This is plus 2, minus 2 1/3, so I can make that minus 2/3. What is this? Not so easy because we have a fraction. What is this? 10 minus 4.5 is 5.5. 5 3/6 minus 2/6 is 5 4/6. Whoops. 5 3/6 minus 2/6 is 5 1/6. So over here we have 5 1/6. We're subtracting a negative 4/6, so we get 5 5/6. So this whole thing is 5 5/6. And remember, that's just the area of this circled part down there.
Did you already do the plus 10?
Yes. I started with 10, subtracted 4.5 to get 5.5, and then subtracted 1/3.
Okay.
Well, that can't be right. Oh, yeah, no, 5 1/6 is correct for this part in the bracket. Over here, this was negative 2/3, which is being subtracted, so I'm 5 1/6 plus 2/3 is 5 5/6. Okay, let's do the second integral. First of all,
so,
let's simplify it.
hold on. Will you go up a little bit?
Yeah.
Or down, whichever way you just went?
Can you see it now?
Yeah. So
Okay.
this is 5 1/6 minus 2 2/3 equals 5
No,
1/6.
no. It's minus a negative 2/3.
Oh, okay. Okay, yeah, there we go. All right, good.
So now we have to do the same thing for this integral, which notice is not the same function, and it's going from -1 to 1. So first of all, let's get rid of these parentheses. So it turns that into a plus 10. Now let's integrate it.
Sorry.
It's all right. I know you know how to do this. So there's our function after we've integrated it, and we have to evaluate it from -1 to 1. So now I'm going to move the whole screen down so I got some room to write here. So we had 5 5/6 plus whatever this is. So let's go through the evaluation. I believe myself that the simplest way is not to try to simplify this on the run. It's to plug it in and then go back and simplify it. Otherwise, you're trying to do too many things at once, if you know what I mean. So plug in that.
Okay, -1/3. -9/2.
Positive 9/2.
And then -10.
Positive 10.
Oh, we're doing 1 or -1?
We're doing 1. You always do the top one first.
Okay.
And then we're going to subtract from that the bottom one. So what's the bottom one?
Bottom one would be 1/3 minus, no,
Plus?
that'd be plus 9/2 minus 10.
Okay. Okay, so again, this is the same as it was. Oh no, this is 14.5 minus 1/3. So it's 14 3/6 minus 2/6. So this becomes 14 1/6 on that side. And this side becomes, I think this is the same as that was, which is, let's see, that's -5.5 plus, so we have -5 3/6 plus 2/6, which becomes -5 1/6. So this whole thing becomes -5 1/6. So the area to the right of my cross point is 19 1/3, or let's say 2/6. I've got to add it to that. So those two numbers, which is 25 1/6, should be the answer.
So this right here equals 19 1/3.
19 2/6. Yes, 19 1/3.
Okay.
Do you have an answer for this one?
Yeah. It equals, I gotta find it.
Oh, I hope it's not.
151/6.
How much?
151/6.
That's 25 1/6. Okay?
So that works?
Yeah. I'm glad we got the right answer, because if you don't get the right answer there, it just means that I've done something wrong with my algebra, my arithmetic, really. It's so easy to make a mistake. You have like 14 steps to go through here. I bet there were. I bet there were 14 steps, and if you get one of them wrong, you're going to get the wrong answer.
Yeah.
So you have to be very, very precise.
Okay, so this one says, approximate the area under the graph of f of x and above the x-axis with rectangles using the following methods with n equals 4. And f of x equals e to the x plus 2 from the intervals x equals -2 to x equals 2. And then part A says use the left endpoints, B use the right endpoints, and then C the average between them, D the midpoints.
Huh, interesting. I have not studied average RAM. Only 3 that were in my book are left RAM, right RAM, and mid RAM. I can see why you'd want average. Average is logical. Okay, so when x is 0, this is 3. And this looks something like this. And we're going from -2 to 2. And we're going to use rectangles. Let's tackle the first one. There's the left RAM. Now this is something else that it's really important you understand the concept here. I think that's why they put so much effort into it. We have to add up these 4 rectangles. What's rectangle number 1? What's its base? What's its height?
So base would be 1.
Correct?
The height would be f of 1.
No, f of -2. In other words, we're talking about that height right there because we're using left RAM. In other words, if we were using right RAM, we'd be talking about this height, f of -1. When we do the right RAM method, I'm going to draw this differently, and the height of this first rectangle would be f of -1. Okay, in the second rectangle, what's its height? The base is 1 in all of them. So this would be f of what?
F of -1.
The third rectangle?
1 plus.
Whoops, hold on. Let me erase these 1s, which we don't really need. Okay, so we got f of -2 plus f of -1 plus, must be f of 0, plus f of 1. You see why? In other words, the height of that first rectangle is f of -2. The height of the second one is f of -1, and so forth and so on.
Yep.
What is f of -2? You want me to use? Yeah, you might be able to do this on your calculator better.
Yeah. Let's see. The answers are in decimals, so that's fine. E to the -2 plus 2, 2.1 -1353.
Okay.
And then -1, 2.367. And then the next one is 3. Got that.
Let's see. This is 4.7. What is E? 2.7.
Yeah, it's 4.718.
0? Oh no, we just need, we got 4 places on this first number here. Only 3 on the other. Is that going to be okay?
Yeah, it should be fine.
Okay.
Let me do the...
Do you have an answer? What's your answer?
The answer, sorry, I didn't hear you, is 12.22.
Okay. I'm sure if you add up these 4 numbers and round it to the nearest hundredth, you'll get 12.22.
Yeah, I'm gonna do
Probably ought to verify that.
Yep, 12.22.
Okay. Now, right RAM. I could go back and draw these triangles. Notice I've got to draw it a little different. These rectangles. The height of this first rectangle is based on the right side of the triangle. So it's going to be that. So what's the formula going to be for the first rectangle? F of minus 1. F of minus 1. Plus the second rectangle is going to be f of 0 plus f of 1 plus f of 2. Notice that the last rectangle's height is based on the right part of the graph. So this point right there is f of 2. So let me just substitute. We got 2.367 plus 3 plus 4.718 plus f of 2. What is that? What's e squared plus 2?
It is 9.389.
What do those 4 numbers add up to be? It's going to be bigger.
19.48.
Really? That much bigger?
Yeah.
That's huge, isn't it? Okay. So our conclusion is the average RAM is going to be better approximation, because the average RAM, I'll just take the height f of minus 2 plus f of minus 1 and divide it by 2. Okay, so let's do the average RAM next. Average RAM, the average height is going to be f of minus 2 plus f of minus 1 divided by 2. It's kind of like the trapezoidal method. It's going to end up being that, kind of like that. How is the average different than the M? Oh, the M is halfway between. No, the M, okay, this is going to be right. You see where I'm going with this?
Yeah.
Okay, let's talk about mid-RAM. What's the difference between mid-RAM and average RAM?
The midpoint's not always the average.
Exactly. What is the midpoint?
Halfway between them.
No, I think that would be this same expression.
And they're different answers too.
The midpoint is going to be f of 1.5. Plus f of minus 0.5. Notice that each of these on the x-axis is the midpoint. In other words, that's the midpoint of that rectangle. So the height of that rectangle is going to be f of minus 1.5. So there's the difference. Now we need new numbers. I don't know. Can you see what the difference is here between average and mid?
Yeah.
Average, you have to add the 2 and divide by 2. Whereas mid, you're taking the function and evaluating it at the middle between the two x points.
Okay. So like the next average one, if I just want to get the next interval, f of negative 1 plus f of 0 divided by 2.
Yes.
Okay.
All the way to the end, to the fourth one. The fourth one's going to be f of 1 plus f of 2 divided by 2. And notice that doesn't necessarily give you the same point. In one case, there's the mid right there of that fourth rectangle. But the average might be closer to up there. So it's going to give us a different height on that rectangle.
So, again, because I'm a little confused with the midpoint one.
Okay, let's evaluate the midpoint. What is f of minus 1.5? It's e to the minus 1.5 plus 2, whatever that number is. And the width of the rectangle is still 1, so I don't need to evaluate that. This is going to be e to the minus 0.5 plus 2 plus e to the 0.5 plus 2 plus e to the 1.5 plus 2. So there's your mid-ram right there. You know, I'm not 100% sure that I've got these differentiated right.
I'm going through this right now.
Okay. In other words, I may be describing these backwards. Mid-ram could be the f of minus 1.5, the more I think about it, and average ram might be the other one. I think the only way I'm going to know the difference in terminology is to have you come up with an answer and look and check it against your answers. So we'll know which is average and which is mid. I'm really not sure at all now that I think about it. I've never given these that much thought because they're such approximation techniques that I would never use.
All right, now I'm going to add them together.
Okay. You almost certainly have to get a number between 12 and 19, because either of these is going to be far superior to left ram or right ram.
So you did it correctly.
Okay.
14.96.
And that's average?
No, 14.96 is the midpoint. And the average is 15.85.
And you got the 14.96 doing the mid, those numbers?
Correct.
Okay, good.
All right, so that one's good. And then,
One of the advantages of doing it the way they're doing it is that as soon as you start doing integration as net accumulation, you realize that you have to do that not just with areas under the curve, but with work. If you have a variable force and you're trying to calculate work, you have to divide it up into increments of work. And each increment can be as small as you want, and it's going to approach zero, and then you add them all up. So that's the whole concept of integral calculus, is adding up tiny little increments always. Same things with volumes of solids of revolution.
Okay, so this one says use substitution.
Okay.
To evaluate the integral, and then it's from 0 to 1, and the function is square root of t to the 7th plus 6t.
Okay, now before you say anything else, I'm going to guess that this whole thing is being multiplied. I'm going to guess that this whole thing is being multiplied by some order of t to the 6th plus 6.
Correct.
Because that's the derivative of the inside.
Yeah. Parentheses 7t to the 6th plus 6.
In fact, that's the exact derivative. So work me through every line of the U substitution.
I'll write that down too. Okay, so U equals t to the 7th plus 6t.
What's next?
And then, for the next thing, so forth, du over dt.
Yes. Take the derivative of U.
And that is going to be 7t to the 6th. Oh, yeah, okay.
And now I move my dt to the other side.
And solve for du.
Solve for dt. In other words, it's dt we have to substitute for.
And dt equals du over 7t to the 6th plus 6.
Okay, so now let's write this as a U integral. I'm going to leave the limits of integration off for a moment because I got to explain how that works. Once we write this as a U integral, I actually have to figure out new limits of integration based on this. In other words, instead of going from 0 to 1, I'm going to go from 0 to 7. Because that's what U does. When t goes from 0 to 1, U goes from 0 to 7. So let's get that straightened out first. Now what's the rest of it?
Okay, so t to the 7th, or U.
That's this part.
Okay.
And then I still have, I haven't done anything with this yet, so I have to leave it there for the moment. Now what?
Du over 7t to the 6 plus 6. And
now I can cancel that out, and now I have a very simple integral from 0 to 7 of U to the 1/2 du. What's that?
Hold on, why is it 0 to the 7th?
Well, I've got two choices here. I can either notice that it's no longer an integral of t, it's an integral of U. So when t was going from 0 to 1, what was U doing? Well, when you plug in 0, u is 0. But when you plug in 1 for t, this is 1 plus 6. So u actually goes from 0 to 7, not from 0 to 1. And I'm going to evaluate this thing as an integral of u without resubstituting back in for t. If I want to substitute back in, then I can use the old limits of integration. But it's actually going to be easier to use the new limits of integration. What's the integral of u to the 1/2?
Would be no, it wouldn't be natural log, would it?
No. Add 1. Always think the power rule first.
Okay, so u to the 3/2, and then it's 2/3.
Notice that even if you have this, and you were to think of the power rule first, you would realize immediately that you got problems. Because when I add 1 and try to divide, I'm dividing by 0. So this is the only integral that is not using the power rule. This is natural log of u. But anything else other than that exponent of -1 is just the power rule. So notice that this is going to be actually easier to evaluate as a function of u than it is as a function of t. If I were to go back and substitute this expression for u and evaluate it from 0 to 1, I think that's a harder evaluation than evaluating that. They're both going to give you the same answer. And it's a total choice on your part whether you want to change the limits of integration and then evaluate the integral as a function of u, or you want to resubstitute for u and go back and evaluate it from 0 to 1. Either one works. Either one's fine. I'm not sure what the advantages or disadvantages of each are. So what's our answer?
14 root 7 over 3.
How'd you get 14?
That's just what the answer is.
Oh, that's the correct answer. Okay. See if this is equal to that. I thought you had multiplied the 2 times the 7. Well, what was your answer again? Let me write it down. 14 root 7 divided by 3. Okay. You know, that doesn't look right. You can't multiply this 2 times this 7. You get the root 7 here, but it's cubed first, and then multiplied by 2. Is this number the same number?
Might be, I'll check.
Notice that I do have to subtract out 0, but when I substitute 0 for u, I get 0, so I don't have to concern myself with the back end of that.
Yeah, it's the same number.
Okay. I wonder if we would have gotten that had we substituted the function back in. Because it's not immediately easy to simplify that to this. It doesn't follow to me at all that that's equal to that. You got the root 7, but it's also 7 cubed, and then the square root of that, times 2/3. But I believe that it's the same. Okay, what else you got? Now, I am kind of curious as to whether or not you could get it in a radical form like that. In other words, the way we did it, in other words, if you do it the way we did it, how do you simplify that to this number? You could certainly come up with a decimal, and this can be converted to a decimal, but what if their answer isn't allow decimals? In other words, if it was one of those MyLab things and where you had to put it in radical form, I'm not sure I know how to get this to look like this, even though it looks like it should be simple.
Yeah.
Huh. Oh, yeah, I know how to do it. Sure I do. It would be it would be the square root of 7 cubed, and multiply that by 2/3. And this is going to be apparently, oh yeah, you could take the 7 out, leaving behind the radical 7. Okay, I get it now. Yeah. So it's 14 radical 7 over 3. That's not that hard a simplification at all. Much simpler than I thought it was going to be.
Wait, what was the last step on that?
When you have the square root of 7 cubed, this is the vital step. That's equal to 7 times the square root of 7. Because notice that if I take 2 of those cubes, 7 times 7, that comes out as a 7.
Okay.
Okay. So, and then we have 2/3 times that. So the 2 times this 7 is 14/3 times radical 7.
Got it. Okay. That helps a lot.
And that they would want that simplified. They wouldn't want you to give that answer as 7 to the 3/2. Their answer was much better.
So there's 6 minutes, but I have another question if you wanted to do it.
Sure.
Okay, so use the definite integral to find the area between the x-axis and f of x over the indicated interval. Check first to see if the graph crosses the x-axis in the given interval.
Okay.
And then it's f of x equals 5 over x minus 5 over e. And then it's semicolon, bracket, 1 comma e to the third. So I think that's like the interval.
So we're going from 1 to e to the third?
Yes.
So this is the function. F of x is 5 over x minus 5 over e?
Yeah.
Okay.
And the answer.
Yeah, let's look at it first. All right.
5 over e plus 5e squared minus 15.
Okay. Let's first of all graph that on Wolfram alpha. Five divided by x minus the quantity 5 divided by e. Now you understand why it's important as to where it crosses the x-axis? Because if, let me just draw a quick example here. If I were to graph the area from 0 to 5 by taking the integral of that function from 0 to 5, it's going to count all of this area as negative, all of this area as positive, and give me a net number. In other words, the area under the x-axis is negative. So if you want the exact area of my shaded area here, I have to take the negative of that area, add it to the positive of that area. But in this particular case, it doesn't appear to cross the x-axis in the interval that we're talking about. the interval is 1 to e cubed, which is way out here somewhere, does not cross the x-axis. It's asymptotic with, what is our horizontal asymptote here? Actually, you know, it might. It does cross the x-axis. If we look at this one down here, notice it's got an expanded, so it does cross the x-axis right there. So we want to do this in 2 intervals. We want to go from 1 to wherever it crosses the x-axis, and then take the integral of the same exact function from that point where it crosses the x-axis out to e to the third, and add that to the first one. All right, so this is what we're looking at. Where does it cross the x-axis?
Set equal to 0. Not sure how to solve that.
Well, that's correct. If 5 over x minus 5 over e equals 0, then 5 over x equals 5 over e. It crosses it at e. Okay? So we're going to go from 1 to e of this function, 5 over x minus 5 over e dx. That's a positive area. It's above the x-axis. Plus, I want to add the negative of the next integral, which is below the x-axis, going from e to e cubed of the same function Notice that if I were to do that alone, I would get a negative number for the area.
Mm-hmm.
So that's why I put a negative sign in front to make it positive. Okay? So it's like that. You can see why our answer is going to come out to be what it came out to be over here. Let's start integrating. What's the integral of that? I'm going to write it all the way over here on the left. Now, let's do this whole thing first, not the negative sign, the first integral, so we don't get confused. It's the antiderivative of 5 over x.
So that would be 5x to the negative 1.
5 natural log x.
Okay.
Yes, because it would be 5x to the negative 1, and if you try to use the power rule, it's not going to work because you're going to be dividing by 0. So that's the one time, whenever you find yourself dividing by 0, the answer is natural log of x. Okay?
All right.
What's the integral of minus 5 over e?
5
No. Yes, minus 5 over e x. Okay? So I need to take that quantity and evaluate it from 1 to e. Let's come up with that because it's pretty easy. When you substitute in e, what do you get? What's the natural log of e?
2.14. Oh, the natural log of e is 1.
Yes. So the first term here is 5 minus 5e over e, 5 minus 5. So that, and remember, I'm not dealing with this right-hand integral yet. I'm still evaluating the left-hand integral.
Mm-hmm.
Now I got to plug in 1. What do I get? What's the natural log of 1?
1.
0. Log of all logs of 1 are 0, because the base raised to the 0th power is always equal to 1. So when I plug in 1 here, this term becomes 0. Now I got to plug in e again. Well, that's 1. So the second part is
5 over e.
Yeah. Oh, there's nothing more to plug in. Yeah. It's like that. So this is 0. That's 0. So 5 over e this is 5 over e for that integral.
In a calculator, would you just do 2.14?
No, notice your answer is in e.
Yeah.
We don't want to convert this to decimal. We're going to end up with their answer, but we got to do it leaving everything in e. So far, we got 5 over e, which is this term right here, which means the answer for this over here is going to be 5e squared minus 15.
Wouldn't it be negative 5e?
Yes, it'll be negative 5e squared plus 15. Okay, I shouldn't really have erased it, because this was 5 natural log of x minus 5 over e to the, or x, which is the same integral as it is over here, only now we have to evaluate it from e to e cubed.
What was the lower limit of the first one?
1. Because in the
Zero
brackets up
minus.
in the brackets up here we were going from 1 to e cubed. But from 1 to e, it's above the x-axis. From e to e cubed, it's below the x-axis.
No, I mean like for the upper it was 5 minus 5. The lower was 0 minus 5 over e.
Yeah, because there was an x there and it was 1. So yes, 0 minus 5 over e times 1. I forgot to write that 1 in there. Okay, so let's evaluate this and make sure we get the negative of this.
So I guess my question is, why is it not negative 5 over e?
Because it was being subtracted. In other words, you take the evaluation at the upper limit and subtract off the evaluation at the lower limit, and the lower limit was minus 5 over e, but it was being subtracted from 0, which turned it into a plus 5 over e.
Okay.
Okay, now let's evaluate this expression between these two limits. What's the natural log of e cubed?
So you said the natural log of e is 1, so 5.
So the natural log of e cubed would be e squared. In other words, when I say the natural log of e cubed, e to what power is equal to e cubed? Well, it's 3. Hold on a second. Hold on a second. What is the natural log of e cubed. It's got to be e squared.
It's 3.
It is 3. Yeah, because if we take that exponent down, okay, well, it's not what I expected, but okay, so we've got 5 times, oh, that's where we're going to get this 15 from. So we got 5 times 3 minus, oh, this is where we get the x squared term from, minus, so that's evaluated at e cubed, right? And then we have to subtract from that the evaluation at e. Well, we know that that's a 5, and that is a 5 also. So this evaluation is 15 minus 5e squared. Added to the first one, notice that this number is a negative number. That was the area under the y-axis and this function. So it's negative. So for me to add it to the area that was positive, which was 5 over e, yeah, I have to flip the signs and make it plus 5e squared minus 15, which was your answer. In other words, if I want to turn this into a positive area, I just make it 5e squared minus 15. And then I add that positive area to my first positive area to get the total net, not the net area. The net area would really be the positive area minus the other area. But if I want the absolute value of the area between the function and the x-axis, then I have to do it this way. And I have to add that second part. And notice that if you integrated from 1 to e cubed, you're going to get the net. You're going to get this minus these two numbers. In other words, it won't subtract off that negative area. It will add that negative area. You understand what I'm saying?
Yeah.
Okay. In other words, if I take that and integrate it from here to here, I don't get this area plus this area. This area comes in negative. This area comes in positive. And I get a net if I integrate from this point to this point. They don't want a net. They want the total area. So we have to take this area, which comes in negative, change the sign on it to make it positive, and add it to the other positive area, which is basically what we did.
All right.
Okay.
Thanks for helping me on that last one.
Yeah. Yeah, no problem. Let's see. We have a Thursday session. I think it's on there at 5, but you want to change that? I can do any time. I'm not playing golf Thursday, so I think you liked 5:30 to 7 was your preferred. Is that right?
On Thursday, 5 to 6:30 is good.
Okay. We'll leave it like that then.
All right. Thank you so much.
You're welcome, Sean. I will talk to you Thursday at 5.
All right. Have a good night.
You too. Bye-bye.